Hello and welcome to today's lesson. We're going to continue on the topic of transformations and look at compound vectors. In this lesson, we'll be focusing on the concept of vectors and how to combine multiple vectors together. Here's an outline of what we'll cover. We'll start by understanding what a compound vector is and how we can combine multiple vectors using a few different methods. Next, we will use some examples to understand some key properties of vector addition. Finally, we'll look at the importance of vector operations in some worked examples. Before diving into compound vectors, let's briefly review what a vector is. A vector is a quantity that has both magnitude or length and direction. Vectors are often represented graphically by arrows, where the length of the arrow represents the vector's magnitude, and the arrow's direction indicates the vector's direction. In notation, vectors can be denoted by a letter with an arrow above it, or simply as a letter in bold. In two dimensions, a vector can be written in terms of its components. For example, v equals vx, vy, where vx and vy are the components in the x and y directions, respectively. Now, moving on to the topic of today's lesson, compound vectors. A compound vector results from combining two or more vectors through addition or subtraction. Let's break down how we perform these operations. Firstly, vector addition involves combining two or more vectors to find their cumulative effect. There are two primary methods to perform vector addition: the graphical method and the analytical method. We will begin by looking at the graphical method, which is sometimes known as the head-to-tail method. The first step is to draw the first vector as an arrow on the graph. Next, place the tail of the second vector at the head of the first vector. Then, draw the resultant vector from the tail of the first vector to the head of the last vector. For example, let's use the following vectors: a equals 3 over 4 and b equals 5 over 2. We would start by drawing vector a, starting from the origin 0, 0. To the point 3, 4. From the point 3, 4, we would then draw vector b to point 8, 6. The resultant vector a plus b extends from the origin to the point 8, 6. Once again, this is known as the graphical method or the head-to-tail method. Next, we will look at another method for adding vectors known as the analytical method. The first step is to break each vector into its horizontal and vertical components. Then add the respective components algebraically. Let's use the same example where a equals 3 over 4 and b equals 5 over 2. To calculate a plus b, we need to add both top numbers to find the overall horizontal movement, and then add the bottom numbers to find the overall vertical movement. In this case, a plus b equals 3 plus 5 over 4 plus 2, and therefore a plus b equals 8 over 6, which means 8 units of movement to the right, and 6 units of movement upwards. Vector subtraction is similar to addition, but involves finding the difference between vectors, which can be visualized as adding the negative of the vector being subtracted. We will once again start with the graphical method. To subtract vector b from vector a, we first need to draw vector a as normal. Then we need to reverse the direction of vector b to make it vector minus b. Next, we place the tail of vector minus b at the head of vector a. Finally, draw the resultant vector from the tail of the first vector to the head of the last vector. For example, let's use the vectors c equals 9 over 6 and d equals 5 over 1, and see if we can subtract vector d from vector c. The first step is to plot vector c as normal, drawing from the origin to the point 9, 6. Next, we consider the vector d and then reverse the direction as we want to subtract it. This can also be seen as making it negative, so the vector minus d equals minus 5 over minus 1. Then starting from the head of vector ic, we can plot vector minus d. Finally, we can plot our resultant vector of c minus d, starting from the origin and connecting to the head of vector minus d. The resultant vector meets vector minus d at the point 4, 5, and therefore this is the answer to vector c minus vector d. Now let's move on to the analytical method for subtracting vectors. Similarly to vector addition, this method involves breaking down the vectors into their horizontal and vertical components. Then, we subtract the respective components of the vectors. Let's use the same example where c equals 9 over 6 and d equals 5 over 1. To calculate c minus d, we need to subtract 5 from 9 as our horizontal components, and then subtract 1 from 6 as our vertical components. Our final answer would be c minus d equals 4 over 5, which matches the answer from the graphical method. Let's move on to our second lesson objective, where we'll explore the properties of vector addition. A good understanding of these properties is essential for handling vectors correctly. The first property we're going to look at is called the commutative property. Vector addition is commutative, meaning the order in which vectors are added does not affect the resultant vector. Mathematically, we can describe this as a plus b equals b plus a. For example, let's use the vectors a equals 2 over 3 and b equals 4 over 1. If we use the analytical method to calculate a plus b, we would add 2 and 4 to find our new top number, and then we would add 3 and 1 to find our new bottom number. This gives us a plus b equals 6 over 4. If we were to reverse this calculation and work out b plus a, we would add 4 and 2 on top, and then 1 and 3 on the bottom. This would once again result in b plus a equals 6 over 4. The commutative property highlights that the order of vector addition does not impact the outcome. The second property of vector addition is known as the associative property. Vector addition is associative, meaning the grouping of vectors does not affect the resultant vector. Mathematically, we can describe this as a plus b plus c equals a plus b plus c. Let's look at an example of the associative property using the following vectors. A equals 1 over 2, b equals 3 over 4, and c equals 5 over 6. If we wanted to calculate a plus b plus c, we would add 1 and 3 before adding 5 to give our overall top number. We would then add 2 and 4 before adding 6 to find our bottom number. This would give an overall answer of a plus b plus c equals 9 over 12. Now, if we try to calculate a plus b plus c, we would once again add our respective top numbers and bottom numbers. Again, this gives a final answer of a plus b plus c equals 9 over 12. The associative property shows that the grouping of the vectors does not affect the resultant vector during vector addition. By following these steps and utilizing these properties, you can reliably perform vector operations, whether you're solving mathematical problems or applying these concepts in real-world scenarios. Let's start with a simple example of vector addition. Imagine we have two vectors, a and b. Vector a is represented by an arrow pointing from point 1, 2 to point 4, 6. And vector b is represented by an arrow pointing from point 4, 6 to point 9, 8. We want to find the resultant vector. Notice that even though our vectors in this example start at the point 1, 2, not the origin, the process still remains the same. The resultant vector r will be the vector pointing from the tail of a to the head of b. This is the vector that points from point 1, 2 to 9, 8, and so we can break down the components of vector r and find the overall vector value. Our top number will be 8, as vector r shows 8 units of movement to the right. Our bottom number will be 6, as vector r moves 6 units upwards. Alternatively, we could have found r analytically. To do this, we first need to break down the components of vector a and find the overall vector value. Our top number will be 3, as vector a shows 3 units of movement to the right. Our bottom number will be 4, as vector a moves 4 units upwards. This gives us the overall column vector of 3 over 4 for vector a. If we do the same for vector b, we can see that our top number will be 5 and our bottom number will be 2. If we add these vectors, we get a total of 8 over 6, which shows us the value of vector r. Next, let's see a simple example of vector subtraction. Suppose we have vectors c and d. Vector c is represented by the vector 3, 4, and vector d is represented by the vector 4, 1. To subtract vector d from vector c, we can think of subtracting the respective top and bottom numbers. Our resultant vector r equals -1 over 3. We can also answer this graphically. First, we draw the vector c, which can be represented by an arrow which goes 3 squares right and 1 square upwards. We can choose where c starts, so let's draw c from the point 2, 3. Next, we need to think about the vector d, which is an arrow which goes right by 4 and up by 1. As we are subtracting d, we need to reverse the direction of the arrow and then place its tail at the head of c. This takes us to the point 1, 6. The resultant vector can be represented by an arrow from point 2, 3 to point 1, 6. This gives us r equals -1, 3 as it points to the left by 1 square and up by 3. Now let's illustrate the commutative property of vector addition. If we take vectors e and f, where e is represented by an arrow which goes up 6 and right 3 squares, and f is represented by an arrow which goes right 4 squares and up 2. Adding e to f should give the same result as adding f to e. Here we have chosen to draw both arrows from the origin, but remember that it is up to us where we chose to start the vectors. First, doing e plus f, e equals 3 over 6. F equals 4 over 2. Therefore, e plus f equals 7 over 8. Now doing f plus e, f equals 4 over 2. E equals 3 over 6. Therefore, f plus e equals 7 over 8. As we can see, e plus f equals f plus e, demonstrating the commutative property. Finally, let's check the associative property. Consider vectors g, h, and I, represented by arrows as shown on the right. First, let's add g and h, and then add I. When we break the vectors down into their components, we can see that g equals 1 over 4, h equals 4 over 4, and I equals 4 over 1. If we group g and h together first, this gives us 5 over 8. Then we add 4 over 1, which gives a total of 9 over 9. Next, let's add h and I, then add g. This would give us 1 over 4, plus 8 over 5, which results in 9 over 9. Both methods give the same result of 9 over 9, demonstrating the associative property. These examples show how to perform vector addition and subtraction and highlight the commutative and associative properties of vector addition. In today's lesson, we explored the concept of compound vectors and how to perform vector addition and subtraction. We began by defining vectors as quantities that have both magnitude and direction, distinguishing them from scalars, which have only magnitude. We then introduced the idea of compound vectors, which are formed by combining 2 or more vectors. Using graphical methods, such as the head-to-tail method, we demonstrated how to add vectors visually. Next, we moved on to vector subtraction, explaining that subtracting a vector is equivalent to adding its negative. We illustrated this with diagrams and examples to ensure a clear understanding. Additionally, we discussed the commutative property of vector addition, which states that the order in which vectors are added does not affect the result, and the associative property, which indicates that the way vectors are grouped in addition does not change the outcome. Throughout the lesson, made use of a range of examples to secure our understanding of the topic. By mastering these fundamental operations and properties, you can solve complex problems involving vectors more efficiently.